Hey, so today we're going to look at the motion of a particle. So today we're getting really into where, in my opinion, math starts to get really, really exciting. So from now on, for literally most of the topics apart from one, we're going to use calculus in everything. So the motion of a particle. So when it says particle, don't stress and don't literally think it means that we're only talking about atoms moving along. It's just a way that we can express the motion of balls or objects. We just say particle. So, and I've just written that there. It's a particle or body. So the first thing we're going to talk about is displacement. So the displacement of a body is its distance from the origin expressed as a function of time. So if something moves to the right, its displacement is positive. If it moves to the left, its displacement is negative. And when it's at the origin, its displacement is 0. So given that the displacement equation x is equal to 3t squared minus t, find the displacement after 3 seconds. So here we've got the displacement, and it's with respect to t, which is time. So the displacement after 3 seconds is going to be x is equal to 3 times by 3 squared minus 3. So we're just substituting in 3 seconds. 3 minus 3 squared minus 3, which is 24. Part B, the distance, I might do it down here. The distance travelled during the 3rd second. Well, the distance travelled during the 3rd second is everything after exactly 3 seconds and right before 4 seconds. So what we're going to do is find the displacement after 4 seconds. So 3 times 4 squared minus 4. 3 times 4 squared minus 4, which is 44. And then we're going to subtract 3 seconds. That will get us how much we moved in just the 3rd second. So therefore the displacement is 44 minus 24, which is 20 meters. Is that right? Let me just double check my maths there. 3 times 4 squared minus 4 is 44. Good. So the average speed during the 3rd second, well, we know that speed is equal to distance over time. So the average speed is going to be 20 over, the 3rd second is just 1 second, so 20 meters per second. Now we've got to start to get ourselves back into a physics mindset. If you haven't done physics before, that's okay. Really, there's a couple of things that we're going to learn that if you do physics, you'll understand, but we're going to learn it as well. The main thing with this is we're going to look at our little displacement triangle, so displacement, speed, time. So here you can see if you cover up speed, you get speed as displacement over time. So the average speed is 20 meters per second. We indicate that by meters per second, we say ms minus 1, or you could say 20 meters per second like that. It means the same thing. So velocity, well, we should know that from year 10 science, for example, velocity is your change in displacement over time. So it's how much your distance is changing over a certain time period. So another way of saying how much something is changing over time is the derivative. So a cool thing that we can see is that if velocity is change in displacement over time, then your velocity is going to be the derivative of displacement over time. So velocity is dx dt. So velocity can be positive or negative. If your velocity is positive, it means you're traveling in the right direction. If it's negative, it means you're traveling in the left direction. And if it's 0, it means you're stationary. So a particle is moving in a straight line, so that its position is given by x is equal to 5 plus t minus 4t squared. Find the velocity when t is 2. So we know that x is equal to 5 plus t minus 4t squared. So our velocity is dx dt. Velocity is the differentiation, dx dt, which is 1 minus 8t. So velocity is 1 minus 8t we're looking at 2 hours, so we're finding when time is 2. So 1 minus 8 times 2, your velocity is minus 16 meters per second. Another kind of physics idea is the difference between velocity and speed, because they're not the same thing. Velocity has direction. It can be positive or negative. Negative is implying we're moving in the left. Positive means we're moving in the right. Speed does not have direction. So if your velocity is minus 16 meters per second, your speed is just 16 meters per second. It doesn't have direction. We call that a, I think it's scalar. Scalar doesn't have direction, and vectors have direction. If you remember that from physics, if you do physics. But importantly, you just need to know that its velocity is minus 16 meters per second, or you could say its speed is 16 meters per second, but we weren't asked to find its speed, but that's just something extra. A particle moves in a straight line so that its displacement x is equal to 2t cubed minus t squared. Find the time when the velocity first becomes positive. Well, let's find its velocity function. So the differentiation velocity is dx to t, and it's equal to 6t squared minus 2t. Now, when something first becomes positive, that means it's just surpassed that 0 mark. So let's find when its velocity is 0. So 0 is 6t squared minus 2t. You can take out a factor of 2t, and we get 3t minus 1. And that means t is equal to 0 or 1/3. If we graphed the parabola of its velocity, it would look something like this. Here it would be 0, this would be velocity, this would be time, this would be 1/3. Now all down here, your velocity is negative, and up here, your velocity is positive. So we could say that your velocity is greater than 0 when time is less than 0 or time is greater than 1/3. But importantly, we know that time cannot be less than 0. We can't have negative time. We can't go back in time, at least with current technology. So therefore, as t must be greater than 0, t is greater than 1/3. That's our answer. So in a test, you would not need to express that. You would just go velocity is greater than 0 when t is greater than 1/3. And in brackets, you must say that's because time can't be negative, or time has to be greater than 0. Right, acceleration is the final really application of this that we're going to learn. So displacement, velocity, and acceleration. Acceleration, well, we know that acceleration is the change in velocity over time. So it's how fast or how slowly my velocity is changing over a certain period of time. So another way of saying something's changing is the derivative. So if velocity, well, if acceleration is change in velocity, then my acceleration is going to be the derivative of velocity. Now we also know that velocity is the derivative of displacement. So acceleration is also the second derivative of displacement. And we say it's acceleration is equal to 2, I missed it, it's 2, to 2x to t squared. We do pronounce it a bit funny. We don't say d squared x to t squared. We say to 2x to t squared. Now when your acceleration is 0, your velocity is at a maximum or a minimum. And we also might just say that dv to t is equal to 2x to t squared, and it's equal to 0. The idea of velocity being maximum or minimum, you mightn't be as comfortable at the moment with y, and that's because we haven't done the calculus of curve sketching yet. But later on in the year, or next year really, we're going to learn that if you differentiate a function and make that differentiation equal to 0, you actually get the value or the x values of the maximum and minimum points of that graph, or its stationary points. So some notation: time is t. Displacement is x. Now in maths, we don't say velocity is v. We say it's equal to x dot. We don't say acceleration is equal to a. We say it's x double dot. So your velocity x dot is equal to dx to t. And your acceleration x double dot is the 2x to t squared, or dv to t. Now, there are names for the third, fourth, fifth, sixth, and sixth derivatives. Some of them have applications, some of them don't. The next one is jerk, which is x triple dot, and it's the 3x to t cubed. The next one is snap, or jounce, and it's x with 4 dots, x dot 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 dot, and it's equal to the fourth derivative. So the 40x to the power of 4. There's crackle. They do get a bit funny, these names, and they are legit. You can look it up. This is what they're actually called. Crackle is equal to x with 1, 2, 3, 4, 5 dots, and it's the 5x to t to the power of 5. And pop, which is the last one, these are the actual names. X is 1, 2, 3, 4, 5, 6, and it's the sixth derivative, or that's the seventh derivative, or the sixth. Anyway, we don't look at anything past acceleration. I believe the only two that actually have uses, or the only ones that have uses, are these ones. Jerk, sometimes we look at the third derivative, and we can look at when our acceleration is at a maximum, but we rarely do that. And snap has applications in trains and railway engineering, I'm pretty sure. Don't quote me on that, but I think that's where it's used. And crackle and pop, I don't think have any uses. The reason they named it crackle and pop is because you got this common saying snap, crackle, and pop. So they're like, oh, snap, we're going to call the next one crackle and the next one pop. But they don't have uses at that I know of, or that we haven't discovered them yet. So a particle moves in a straight line such that its position x from a fixed point O at a time t is given by x as t cubed minus 12t plus 16. Find its initial position, velocity, and acceleration. Well, we know that x is equal to t cubed minus 12t plus 16. Let's find the equations of the velocity and acceleration first. So x dot is equal to 3t squared minus 12, and x double dot is equal to 6t. So its initial position, whenever you see initial in this, it means when time is 0. So x of 0 is going to be putting 0 into this first equation, we get 16. The velocity, x dot of 0, its initial velocity, is putting 0 into that second equation, we get minus 12. And x double dot, your initial acceleration at 0, is putting 0 into that third equation, we get 0. Find the time when its velocity is 0 and its position and acceleration at that time. Well, we know its velocity x dot. I'm going to just use v every now and then. We don't usually use v, we use x dot. Or we sometimes use v later on when we express acceleration in extension 2 as v to v to t, but at this stage we don't. So velocity is equal to x dot, which is equal to 3t squared minus 12. We're making that equal to 0. Bit of equation solving, you'll get t is plus or minus 2. So therefore t is 2, as t must be greater than 0. I'm not sure whether you actually have to specify that according to the HSC markers, but there's no harm in doing it, just saying as t is greater than 0. So find its position and acceleration at that time. So we're looking at x of 2, which is 2 cubed minus 12 times 2 plus 16. Which is 0. So its displacement is 0 at that point. And acceleration, x double dot, we know that's equal to 6t. So x double dot of 2, so we're finding the acceleration at time 2, is going to be 6 times by 2, which is 12. Now the x double dot Acceleration's notation is meters per second, or ms minus 2, or 12 meters per second squared, like that. But we usually use the first one. Okay. An object is travelling in a straight line over time t seconds with displacement x is equal to t cubed plus 6t squared minus 2t plus 1. Find equations of its velocity and acceleration. So we've got x is equal to t cubed plus 6t squared minus 2t plus 1. So its velocity x dot is the differentiation 3t squared plus 12t minus 2. And its acceleration is 6t plus 12. So just differentiating that twice. Part B, what would its displacement after 5 seconds be? We just substitute in 5. X of 5 is equal to 5 cubed plus 6 times 5 squared minus 2 times 5 plus 1. So substituting that in, which is 266 meters. Part C, what is its velocity after 5 seconds? We're just looking at x dot and substituting in 5. So x dot of 5 is 3 times 5 squared plus 12 times 5 minus 12, which is 123 meters per second. And part D, find its acceleration at 5 seconds. So x double dot of 5 is equal to 6 times 5 plus 12, which is 42 meters per second. Now I was just looking at the question. It doesn't actually tell us that, oh no, it does say it's meters. So yeah, we've got meters there, and then we've got seconds, so we can say meters per second. Okay, stone is dropped from the top of a building. The stone's height h above the ground is h is 80 minus 5t squared. How high is the building? Well, that's just saying what is its height when time is 0. So h is equal to 80 minus 5 times 0, which is 80. How many seconds does it take to hit the ground? Well, it hits the ground when time is 0. Sorry, when it hits the ground when your height is 0. So 0 is equal to 80 minus 5t squared. So solving that, you'll get plus or minus 4. So therefore, t is equal to 4 seconds as t is greater than 0. We're told the velocity is a rate of change to ht of height. Find the velocity function. Well, we know height is equal to 80 minus 5t squared. So h to t is equal to minus 10t. Now the reason it's to h to t and not to x to t is because our notation of the derivative, whatever our function is equal to, h goes on the top, and whatever is actually in the function, or the variable in the function, is on the bottom. So we say the differentiation of h with respect to t, or respect to time, is minus 10t. Now we can also say this is not x dot, but h dot is minus 10t. How fast is the stone travelling when it hit the ground? Well, we know h dot is minus 10t, and it hits the ground at 4 seconds, so minus 10 times 4, which is minus 40 meters per second. Find the acceleration of the stone. Well, we know h dot is minus 10t, and the differentiation of velocity is your acceleration, so h double dot is minus 10. So h double dot is minus 10. Now, putting ourselves into a physics mindset, we know that all objects fall at the acceleration of due to gravity. So their acceleration at which any object falls is minus 9.8 meters per second. So just as a side, it's minus 10 as it's almost gravity. So sometimes mathematicians and physicists, it makes me angry, but we approximate gravity to 10. Kind of like engineers approximating pi to be 3 and e to be 3. Question 6, what a projectile is fired into the air and its height is given by h is 40t minus 5t squared plus 4. Find the initial height. Well, h is equal to 40t minus 5t squared plus 4. So the initial height is when t is 0. So h of 0 is 4. So the initial height is 4. B, find the initial velocity. Well, let's find velocity. Velocity, or h dot, is equal to the differentiation 40 minus 10t. The initial velocity is when t is 0, so h dot of 0 is equal to 40 minus 10 times 0, which is 40. So therefore, the velocity is equal to 40 meters per second. You could also, the h dot is equal to 40 meters per second. Find the height after 1 second. Well, we know h is equal to 40 times by 1 minus 5 times 1 squared plus 4. We're just substituting 1 into our height equation. So 40 times 1 minus 5 times 1 squared plus 4 is 39. Part D, what is the maximum height of the projectile? This is another thing that requires a bit of thinking, but once you're told it, you'll never forget it. If I'm a projectile going up and up and up and up and up and I'm traveling up, well, eventually I'm going to have to start coming down. So as I'm going up, my velocity is slowly decreasing because I'm slowing down, and then I have to start coming back down. But if we think about that logically, if you're going up and then you start to come down, there's got to be a certain point right at the top that your velocity is 0 or you're stationary. So if you throw something up in the air, before it can start coming down, it has to stop for a very, very small amount of time, and then it will start coming down. So the maximum height of a projectile is when its velocity is 0. So we know that h dot is equal to 40 minus 10t. So we make that equal to 0. 40 minus 10t equals 0. Solving that, we get t is equal to 4 seconds. So the maximum height occurs at 4 seconds. So we actually find that height by substituting it into h. So h of 4 is equal to 40 times 4 minus 5 times 4 squared plus 4. Which is 84. Now we're going to sketch the graph of height against time. Now we're only going to sketch the first quadrant, and that's because height cannot be negative and time can't be negative. Now we know it starts at 4 meters, and any projectile, if we fire it up, it's going to look something like that. That's what any projectile fired would look like. We should know that. If you throw anything, it's going to go up and curve and come back down. We know its maximum height is 84. And that occurs at 4 seconds, so we're done. That's my displacement against height against time. Now, something that's interesting to note is that if we go right across here, at this point here, this will be at 8 seconds. So if you fire something up at a projectile and you fire it up, well, we know that its maximum height is at 4 seconds. So the time it takes for an object to go from its starting point to its maximum height, we're told it's 4. And putting our physics mind caps on, that also means the time for it to fall from its maximum height back to where it started is also 4 seconds. So the time it takes for the projectile to go from 4 all the way up to 84 and back down to 4 is 8 seconds. Importantly, it's not 8 seconds down here when it reaches the ground. It would be 8 seconds when it reached the ground if the object started at the origin, but it doesn't in this case. So what we're doing now is we're doing the highlighted questions of 8.12, which is on OneNote. All right, thank you.